You look at a solid block of steel, right? And you think, solid, unmoving. But what if I told you that on the inside, at a level you can't even see, there's a wild, non-stop dance party happening? It's true. So let's dive into this hidden world of atomic motion.
It brings up a pretty big question then. How in the world does an atom move through a solid block of steel? I mean, it's packed tight in there. There are no little tunnels or anything. It sounds impossible. But the answer is a process that is constantly shaping our world, usually right under our noses.
And that answer is diffusion. Now, don't picture a smooth, orderly flow. Think more of a frantic random hopping. Individual atoms just jumping from one spot to the next, right inside that super-organized crystal structure. This is the secret mechanism, the one that lets solid things actually mix and change from the inside out.
Okay, so to really wrap our heads around this, we've got to zoom way, way in. Let's follow the journey of just a single atom. It's a journey that honestly looks like it's going nowhere fast, but believe it or not, this is the foundation of everything we're talking about.
Okay, so picture our little atom. It's got some heat energy, it's vibrating, and then, boop, it makes a little jump to an open spot next to it. Then another jump, and another. But here's the thing. It might jump forward and then immediately jump right back where it started. Every single move is totally random. It's like flipping a coin every single time to decide which way to go. And this is where it gets kind of weird. If you track this atom over thousands and thousands of jumps, and then you average out its position, it's basically right back where it started. It hasn't really gone anywhere. For every step it takes to the left, there's a good chance it'll take one back to the right. Its average movement is 0. Which begs the question, how does anything ever actually move from point A to point B? Aha! Here is the key insight. While its average position is 0, the atom is definitely exploring new ground. The real distance it travels from its starting point is absolutely not 0. And here's the rule. That distance grows with the square root of time. Think about that for a sec. To go twice as far, you don't need twice the time, you need 4 times the time. So yeah, it's slow, but it is making progress. So one atom on its own, it's just chaos, a random walk. But what happens when you've got billions upon billions of them all doing this at once? Well, that's when the magic happens. Out of all that chaos, a surprisingly predictable pattern emerges. It's so predictable, in fact, that it becomes a fundamental law of nature. I want you to imagine a hill, but instead of dirt, this hill is made of atoms. At the very top, they're all crowded together. That's our high concentration zone. Down at the bottom, they're much more spread out. That's low concentration. That slope from high to low is what we call a concentration gradient. Now, remember, every atom is still just jumping around randomly, but just by pure probability, right? There are way more atoms at the top that can randomly jump downhill than there are atoms at the bottom that can randomly jump uphill.
And that simple idea that atoms tend to move downhill is basically the core of Fick's first law. It's a fancy name for a really simple rule. It just says the net flow of atoms, which we call flux, really only depends on 2 things. 1, how easily can the atoms move around? We call that the diffusion coefficient. And 2, how steep is that concentration hill?
So let's just make that super clear. You want to get a big flow of atoms moving? You need 2 things. First, you need atoms that can jump around easily. That's high diffusivity. And second, you need a really steep gradient, a huge difference between the crowded area and the empty area. Makes sense, right? On the flip side, if your atoms are kind of sluggish, or if that concentration hill is more like a gentle slope, you're only going to get a tiny little trickle of flow. Okay, so this isn't just some abstract physics concept. This has real, tangible consequences. Let's take a look at what happens in the real world when we try to make a material, but things are happening way too fast for diffusion to keep up. Check this out. This is a microscopic image of an aluminum-copper alloy. See those beautiful kind of tree-like patterns? That's not just for show. This is a story, frozen in time. So what do you think? What does this pattern tell us about that atomic dance we've been talking about as this metal was cooling down? All right, here's the play-by-play. As this alloy started to cool, the first things to crystallize were rich in aluminum. That process literally pushed the copper atoms away into the liquid that was left over. So now the liquid is super rich in copper. Now, if this happened slowly, diffusion would have time to spread that copper out nice and evenly. But it didn't. The cooling was too fast. Diffusion just couldn't keep up. So what we get is this layered, uneven structure. We call it a chord structure that's literally frozen in place. It's perfect visual proof of diffusion, or in this case, what happens when it's too slow. Okay, so we've established that atoms jump. But how? What does it actually take for an atom to make that move? Well, it needs two things. It needs the energy to actually make the leap, sure, but just as important, it needs an empty spot to land in. And that empty spot is the whole secret. We call it a vacancy. The best way to think about it is like an empty parking spot in a completely full lot, or an open space on a packed dance floor. It doesn't matter how much energy you have. If every spot around you is taken, you're stuck. You've got nowhere to go. These vacancies are the absolute key that allows the whole dance to happen. So it turns out there are basically two main styles to this atomic dance. The first is called substitutional diffusion. This is where an atom, say a copper atom in aluminum, has to literally wait for one of its neighbors to move out, leaving an empty spot, before it can jump in. As you can imagine, this is slow. But then there's a second way, a super fast shortcut. It's called interstitial diffusion. This is for really small atoms, like carbon and iron. They're so small, they don't have to wait for a main spot to open up. They can just zip through the little gaps between the main atoms. There are way more of these little gaps available, so it is just incredibly fast in comparison.
And this is where it all pays off, right here. Understanding this atomic dance isn't just for, a physics textbook. It's how we engineer materials with absolutely incredible properties. By mastering diffusion, we can literally build a stronger, better world.
Okay, let's look at a classic engineering puzzle. We all know that adding carbon to iron gives you steel, and steel is way harder. But there's a catch. If you make the entire piece of steel high carbon, it becomes brittle. It can shatter. So the ultimate challenge is, how do you get the best of both worlds? A super hard surface that resists wear and tear, but a tough inner core that can take a hit without breaking.
The answer? You guessed it. You use diffusion. The process is called carburisation, and it's brilliant. You start with a piece of plain low-carbon iron, you put it in a chamber with a ton of carbon, and then you crank up the heat. We're talking like 1,000 degrees Celsius. What does this do? Well, you've just created a massive concentration gradient. Tons of carbon on the outside, almost none on the inside. And that intense heat gives those carbon atoms a huge boost of energy, letting them use that super fast interstitial diffusion to zoom right into the surface of the iron.
And the result is just perfect engineering. By controlling the temperature, the time, and the concentration, you create a part, like a gear for instance, that has exactly what you need. The surface is now loaded with carbon, making it incredibly hard and wear-resistant. But the inside, the core, it's still low carbon, tough, and able to absorb shock. It is the absolute best of both worlds, all thanks to controlling this atomic dance.
So think about it. We went from the completely random, chaotic walk of a single tiny atom, all the way to the precision engineering of high-performance materials. Diffusion is one of those fundamental processes that is quietly shaping everything around us. So it leaves us with a big question, right? Now that we can understand and even control this atomic dance, what are we going to build next? What problems will we solve? What incredible new materials are just waiting for us to design them?